Section 4.1, Antiderivatives. We have three objectives in this section. The first one is to find the general antiderivative function. The second is to use basic integration rules to evaluate indefinite integrals. And finally, the third one is to use antiderivatives to solve simple initial value problems. So we begin with the definition of antiderivative. What is an antiderivative? We say that the antiderivative of a small function f of x is the set of functions capital F of x plus c such that the derivative of the capital F of x plus c is equal to the small f of x. So something is called the antiderivative if its derivative will give us the small function called f of x. Typically, what we're going to be doing in this chapter is finding the antiderivative of the small f of x. So we are going to be searching for the capital F of x ourselves. So that's the whole point of this whole chapter. And the process that we're going to be doing is called integration or antidifferentiating. So antidifferentiating is basically the process by which we look for the antiderivative of some little function f of x. So notice how the small function f of x is the derivative of the big function capital F of x. In other terms, the derivative of this big capital F of x plus the little c is equal to the small function f of x. Now this c over here is called the constant of integration. We always add it to the problems because its derivative would be technically 0, so it's always required to write down the plus c at the end. There's going to be some notation that we use for these problems to make life a little bit easier, and it's the notation that you're seeing in the middle of the page over here. There's going to be something called an integral. So this integral symbol is basically like a stretched out capital S, so very nice and smooth. We write the little function whose antiderivative we want to find, and then we add this thing called the dx. It's part of the integrand, so this portion over here is the integrand. The whole thing is known as the integral of the little function f of x, and we usually are required to find the answer, which is what we call capital F of x plus the c. This is the general antiderivative of the small function f of x. So, in other terms, we are trying to undo the work of derivatives in this chapter. So we're doing the opposite process. So what we're given is a derivative of something, and we want to know what was the question that we differentiated to find the little function f of x that's given to us in the problem. In the first example, we are given both the capital function f of x and the little function f of x, and we're told to verify or to show that the big f of x is in fact an antiderivative of the little function f of x, which is x squared plus 12x minus 4. So ideally, your job in this chapter is to find this answer given the little function f of x with the extra new notation mixed in. So how do we confirm that the big f of x is in fact the antiderivative of the little f of x? To check, we have to verify the requirement that the derivative of the big f of x, so the derivative of the big f of x, plus some constant of integration little c, is in fact equal to the little f of x. This is what we have to confirm. We have to check that this is true for the given capital F and little f. So in other terms, so we need to check that the derivative with respect to x of, in this problem, 1/3 x cubed plus 6x squared minus 4x plus 3, and also we're going to add plus c because the derivative of c is going to be 0. We want to confirm that the derivative of this quantity is the given little f of x. Is it possible? Is it true or not? So let's check what is the derivative of 1/3 x cubed. So according to our derivative rules, the 1/3 is just going to hang out. The derivative of x cubed is going to be 3x squared. So this is the standard procedure that we learned in the previous chapters. Then we have a plus sign, so we're going to ignore the plus sign, and we're just going to proceed to the next term, which is the 6x squared. What's the derivative of 6x squared? The derivative of 6x squared is going to be 6 times the derivative of x squared, which is just 2x. Next, we have a minus sign, so we're going to, again, ignore the minus sign and move on to the term next to it, which is the 4x. What's the derivative of 4x going to be? Well, 4 is going to go for the ride, and the derivative of x is going to be 1. So that's the usual. And finally, we have the plus 3. So again, there's a plus sign there, so we're going to ignore the plus sign and find the derivative of 3. The derivative of 3 is going to be 0. And finally, last but not least, is the plus c. What's the derivative of a constant? Well, we just saw that the derivative of 3 is 0, so the derivative of plus c is also going to be just simply 0 because c is technically a random real number. Well, to clean up this mess and confirm, let's just go ahead and multiply some numbers. So we have the 1/3 multiplied with the 3x squared. The 3's are going to cancel out there. We just get simply x squared. Then we have the 6 times the 2x. Well, that's going to be 12x. So that's the end there. And then 4 times 1 is going to be 4. And finally, 0 and 0 at the end. Those things don't matter. We're just not going to write down 0. So as you can see, this is the answer we got, and this matches with the little function f of x that was given to us. So this is in fact equal to the little f of x, so we can say yes, the person who found this and is claiming that this big function f of x is the antiderivative of the little function f of x is correct. They are in fact correct in their claim. And so how do we present this at the end? How do we say this in fewer words and using symbols? We say this. We say that the antiderivative of the little function f of x dx is the big f of x plus c. So the capitalization here does matter. So in fact, you have to pay attention to whether the letter is small or capitalized, and it means different functions. So in other terms, what we're saying is that the antiderivative of the x squared plus the 12x minus 4 with respect to x is in fact equal to 1/3 x cubed plus 6x squared minus 4x plus 3. And you can also add the plus c if you want. We usually are going to do that in the problems. So our work is going to look like what's in this box over here at the end. I'm going to give you this part, and your job is going to be to find the opposite part by using certain rules that we will present in the next page. Now, before we look at the rules, let's see if you have a little bit of intuition. I want you to pause the video for a second and try to answer this second question that we have, where it says, name an antiderivative function for the little f of x, which is equal to 2x. So can you pause the video for a second and think about this for a moment? Is there a function out there that we call big f of x? So is there a function called big f of x that you can add a constant to it whose derivative will be the little function f of x, which is equal to 2x. Is it possible? Can you guess what that big function f of x should be? So maybe you did pause the video, maybe not, we'll find out. If you did pause it, did you come up with a certain guess for what the big function f of x is? So just recall from memory, from the previous chapters, what variables or what functions did you differentiate to get at the end just simply 2x? And if you guessed that the capital function f of x should be equal to x squared, then you are correct. So to confirm, let's find out, is it true that my guess is correct? So how do I confirm that my guess is correct? Well, I just take the derivative with respect to x of x squared plus c. Is it equal to the little function f of x that is given in the problem? Well, we already know from the previous chapters that the derivative of x squared is just simply 2x, and the derivative of plus c, the c is a constant, the derivative of constant is always 0, so this is in fact really equal to 2x, which is in fact the little function f of x. So our guess is that the antiderivative, or one possible antiderivative, is x squared. Now remember, I could have also said x squared plus 1, or x squared minus 5, or x squared plus 7, or x squared plus really any number, any real number would have worked. And that's why we're adding the plus c over here, because its derivative will eventually become 0 and it will disappear, giving us just simply the 2x in front. So that's why we always add this constant of integration, little c. And so sometimes you'll see me writing, whenever I present the c that wasn't already in the problem, I usually write the symbol. C is a real number. So this is fancy notation to say that c is a real number. So what am I writing over here? I'm writing c first, and then this funky looking e symbol. This is basically how we say that a number is part of a set. So I'm saying that the C that I'm writing on the page, this constant, belongs to the real numbers. And for the real numbers, we use a special symbol. It's like an R with a double edge on the left side. This is the symbol for real numbers. It's a big capital R. So I usually will write this next to any problem where there wasn't a C at the beginning, but I added the C myself, just to remind the reader that whatever C I'm putting there is really just a constant. Don't treat it like a variable, treat it like a regular good old constant, right? Like a regular number from the real world. Okay, so now if you don't like the guessing game and you'd like to know the antiderivative in general, given any kind of variable or any kind of expression, well, you're in luck because we have a list of theorems that can help us when we're looking for antiderivatives. My recommendation is to write down these rules on a separate piece of paper, just like you did when you were learning the derivative rules, so that way you can have them handy and keep referring to them whenever you need them. I'm going to use them throughout the whole chapter, so it's good to memorize all the formulas on this page, but we're going to use them so often that it's going to become like second nature. But we begin with the integral of a constant. So if I have a constant and I want the antiderivative for it, so in other terms, if I have something like the antiderivative of 2 dx, so I just have a 2, it's a constant. What is the antiderivative of a regular number? Well, according to the rule, it's just 2 times an x plus the constant c, the constant of integration. So how do I confirm that this is right or not? Just take the derivative of 2x and see if it matches the inside of the integral. So the derivative of 2x is really 2 times 1, which is 2, and the derivative of c is 0. So 2 plus 0 is going to be the 2 that we see there. So perfect. This is exactly how that problem is going to work. So the antiderivative for a constant is just the constant itself multiplied with the letter or the variable x. Okay, what about if I have an x raised to an exponent, right? Like x squared or x cubed. What would be the antiderivative of something like that? So in other terms, something like x cubed, what is the antiderivative for x cubed? So this is rule number 2. It's called the power rule. And this works as long as the exponent that you have is not -1. So if it's 1, 2, 3, even a fraction, if it's negative, it works all the time except if the number is -1. We have a special rule for that on the next line. But if the power is a random number other than -1, according to the rule, what you're supposed to do is just add 1 to that number. So in this case, I have 3. I add 1 to it, it becomes 4. And then I divide by the same quantity. I divide by the same value. That's what the rule is basically telling me. So add 1 to the exponent and divide by the same number that you get. So in this case, 3 plus 1 is 4. So I divide by 4. And then finally, just add the plus c, as usual, the constant of integration. So this is the rule that we call the power rule, and this works whether you have a positive number or negative number or fraction in the power. It works all the time as long as the power is not -1. So what if the power is -1? Well, that's where we use the next rule. If the power is -1, so if x has -1 in the exponent, then what we're supposed to do is just know that the antiderivative is just ln natural log of the absolute value of x. So that's what the rule says, plus the constant of integration called c. And by the way, sometimes instead of writing x to the -1, you'll see 1 over x written down. This is the same expression. Remember the rule from exponent world. It says if you have a negative in the power, it just means that the quantity wants to be on the denominator. So if I have a -1, that means I have 1 over a to the power of 1, or just simply 1 over a. So that's why sometimes you'll see x to the -1 or 1 over x. So regardless, this rule applies, and it will give us just simply ln of the x, absolute values. So far, what we should know is that the antiderivative constant is just a constant times an x. And if I have an x raised to a power, first of all, the x needs to be in the numerator. So if it's not in the numerator, you have to bring it to the numerator. If you have a problem like antiderivative with 1 over x squared dx, the rule does not apply. You have to rewrite the problem first before you can apply the power rule. But if the x is in the numerator, just add 1 to the exponent and divide by the same quantity. Unless the power is -1, then in that case, change of rules and just write down ln absolute value of x plus c. The next rule is the exponential functions rule, right? It tells us what to do if you have an exponential function e to the power of x dx, and this is one of the easiest, most simplest rules. What's the antiderivative for e to the x? It's just simply itself. That's it. And we also add the plus c as usual at the end of all these rounds. So this is the only function in the universe whose antiderivative is literally itself, right? It's just antiderivative for e to the x is just simply e to the x. Now, what if I have a number times an x, right? So what if I have something like, I don't know, 2x cubed? What is the antiderivative of that? So according to the rule number 5, which is known as the constant multiple rule, I am just supposed to ignore the constant. So if I have a constant and a variable, I ignore the constant and just integrate the variable. If I have a constant by itself, I add x to it. But if I have a constant and a variable, the rule is ignore the constant and just focus on the variable and do what you'd normally do for the variable. So in this case, I have 2 times the antiderivative for x cubed. So I just ignore the 2 and I just find the antiderivative for x cubed, which is x4 over 4, because I'm adding 1 to the exponent divided by the same number, and then put a plus c at the end. So this is the answer, and obviously, usually you have to reduce it to lowest terms at the end, but that's what the constant multiple rule basically tells us to do. So ignore the constant if you have a constant and a variable, ignore the constant, just focus on the variable. Now finally, what do I do if I have two x's being added or subtracted to one another? That's where the sum difference rule comes into play. So for example, if I have x cubed plus e to the x, and I'm looking for the antiderivative of them, what am I supposed to do? The rule basically says just integrate piece by piece, ignore the plus or the minus. So regardless of whether there's a plus or minus there in the middle, you just do the same thing. So you separate the problem into different pieces. There was a plus in the middle at the beginning, so just write down a plus now again, and just individually find the antiderivative of each portion. And so again, the antiderivative for x cubed is x4 over 4. The antiderivative for e to the x is itself, and then we put a plus c at the end, and that's basically the end. So this rule works whether we have a plus or minus, so just keep that in mind. This is called the sum or difference rule, and as you can see, we don't have a product or quotient rule. There won't be something like a product or a quotient rule. This is why we're going to learn more advanced techniques later on that tell us what to do when we have a product of x's with other x's. But generally speaking, what we do is we try to FOIL everything out and integrate piece by piece using this sum difference rule. So for now, let's try to find some antiderivatives knowing this rule list that we just talked about. So take a screenshot of the rules or write them down somewhere so you can have them handy and use them in the problems that will come later. In the next few problems, I'm going to write down every single thing that I'm doing just so that you don't get confused. But later on, we're going to start skipping a few steps and a few details. Otherwise, we get too overwhelmed with all the notation that we have to write down. So in example number 3, we are told to evaluate each integral. Another way of saying this is to just simply state integrate. So you might see the word integrate or just simply the word solve. Regardless of what the question is, I'm seeing an antiderivative of some stuff, and I want to know what the antiderivative is, basically. So remember, this part over here is what we typically call the little f of x. So your job is to start with the antiderivative of the little f of x and give me some big f of x plus c at the end. So this is your goal, is to find the antiderivative. And so let's try to do it together here for this first problem. So as I stated, I'm going to write every single detail, and let's begin by first copying the problem itself, and let's analyze what we're dealing with. So I usually copy it just so I can see what I'm dealing with. And so what am I dealing with? I'm dealing with a difference and a sum of basically 3 terms. So according to rule number 6, which is the sum difference rule, I can start by breaking apart each one of those pieces. So I'm going to write down the integral of x squared dx. Then I'm going to ignore the minus and write down an integral for the 8x. Then I'm going to ignore the plus sign and just write down an integral for the 3. So the old minuses and pluses basically are the places where we separate the problem into 3 different integrals. Now, always write down the integral symbol with the dx together. They come together at the same time and they leave together at the same time. So you keep writing them until you actually do the process of antidifferentiating. So adding 1 to the power and dividing by the same thing, and so on and so forth. So it's kind of like, think of it like a set of parentheses. We write the left one and we write the right one at the same time, and they both disappear and show up at the same time. This is the same with antiderivatives. So this antiderivative symbol and the dx, they show up at the same time and they leave at the same time. So I want 1 for the x squared, I want another one for the dx, and I want another one for the 3 at the end. So this is rule number 6, allows me to break the problem apart into multiple pieces. And now I'm going to focus on each piece individually. This one I know how to integrate because it's just the variable with the power. So this is going to be rule number 2. Now this middle one has an 8 times an x, so there's no multiplication sign written down, but we understand and we realize that ourselves. So what do we have to do for this one? We have to ignore the 8. We have to bring the 8 outside of the integral because it has an x next to it. And finally, there's a 3 over here. This is the constant rule. It's rule number 1. We're just going to need to add an x next to it. So the 3 here does not have to exit the integral. So let me focus on bringing the 8 out now and leave everything else alone for a little bit. So I'm going to just copy down everything except the 8 that used to be next to the x. I'm going to write it on the outside. And the 3 I'm going to leave inside the integral because the 3 does not have any x's with it. So all I did here is focus on the middle part of the integral and just separate it into 8 times the integral of x. And this is using rule number 5, which is called the constant multiple rule. So if you have a constant with an x, just bring the constant outside. So now I'm going to think about the x squared. What's the antiderivative for x squared? I'm ready to do that. The antiderivative for x squared is literally x squared plus 1 divided by the same number. Now, if you know 2 plus 1 is 3, and you want to write it right away, that's perfect. Just do that. So if you prefer to write 3 right away here and there, that's okay. For now, though, just to keep it kind of as simple as possible and explain every detail, I'm just going to write down 2 plus 1. Next, I have the negative 8, and there's an antiderivative for x. So what power does this x have? I don't see any power, so I know that the power is really a 1. So again, using the same rule that I just used right now, I'm going to write down x to the power of 1 plus 1 divided by 1 plus 1. So the first number that I'm writing is the original power, and then the rule tells me to add 1 to the existing power. That's called the power rule. So I used the power rule twice, once for the x squared and once for the x. And finally, I have the antiderivative of just simply 3. There is no x there. So what do I do when I have just a constant by itself? I write down 3x. So that's rule number 1, which is the constant rule. Tells me that when I have a constant all alone, just write down 3x. And as part of the anti-differentiating process, we always write down the plus c at the end. And what is the c? I'm going to write down c is a real number so that whoever is reading this will understand that this letter that I'm writing is not really a variable, it's really a constant, so just treat it like a random number. Okay, so the last thing we have to do is just clean up the mess a little bit. So 2 plus 1 is 3, so I'm going to write down x cubed over 3 minus 8. 1 plus 1 is 2, so that's x squared over 2 plus 3x plus c. And in reality, this middle term, I can reduce it to lowest term. So 8 times x squared divided by 2 is really 4. So let's just write down 4 instead. And to make it look as pretty as possible, I'm going to put 1/3 x cubed minus 4 divided by 2 is going to be, sorry, 8 divided by 2 is going to be 4, and then the x squared plus the 3x plus the c. So this is how the problem is going to look, and obviously in the future we want to skip as many details as possible. So typically what we end up doing is we end up skipping the first couple of lines. We do most of that work mentally, and we go directly from the first line all the way to the solution. And if you can just simplify things as you go, that's even better. You can save a lot of time by skipping certain details and not writing them down. But this is the process that we call anti-differentiation. And so in this process, this beginner function is the little f of x, and this function that we're writing in the box is the big f of x plus the little c that we add. Okay, and so you have to remember that the antiderivative of the little f of x dx is the big function f of x plus c. Another way of saying this is that if I differentiate the big f of x plus the c, I should see the answer, which is the little function f of x. So this is two different ways of saying what we just did using the new notation and the old notation. So if you're not sure whether you're doing the problem correctly or not, just take what's in the box and find its derivative. If you get this little function that was written at the beginning, then you did the problem right. If you don't get the same answer, then something went wrong somewhere. Go back and review your notes. Okay, so now that you've seen how to do one of them, try to pause the video and see if you can do the next problem. And I'll give you a second to pause the video. And then after you pause, we'll work it out together again using all the details and all the rules that were stated above on top of the page. Okay, so first things first, there's a difference between this problem and the previous one. The letter here is T, but it doesn't matter what the letter is, whether it's T or X, we treat it the same way. We just do the same usual thing. So the first thing I'm seeing here is I'm dealing with 1, 2, 3 pluses and minuses in total. So that means I have 4 terms. So according to the sum difference rule, which is rule number 6, I can give each one of those pieces its own individual integral. So I can give the 4t cubed its own integral, I can give the 12t squared its own integral, and I should be writing dt over here, and I can give the at its own integral, so integral of at dt, and then finally the 5 gets its own integral as well. So this is the sum difference rules that tells me that I can break my problem that had 4 terms into 4 different simpler problems and just solve each one of them individually. Now the next thing I'm seeing is that the first integral has a 4 next to the t cubed, the next one has a 12 next to the t squared, and the next one has an 8 next to the t. And finally, the last one has just 5, no variable there next to it. It's just the dt at the end. So what I'm going to do is I'm going to ignore the 4, the 12, and the 8. I'm going to basically bring them outside of the integral. This is rule number 5, the constant multiple rule. So first write down the 4, then write an integral for the t cubed dt, then write the 12 down in front of the integral, and then t squared dt. Then the 8 goes outside, and we leave the t inside the integral. And finally, the 5, we can leave it inside the integral. Sometimes, though, some people prefer to write it on the outside. So if you decide to write it on the outside, you're going to have an empty integral. So it's just the integral symbol and then the dt next to it. And when you see that, it might show up in homework problems or on exams or quizzes. Just realize that there's an invisible 1 there. So the antiderivative for 1 is just going to be 5, 1t, and then with the 5 on the outside, you just get back the same solution, 5t. So if you see the 5 with an integral and nothing written down, just remember it's an invisible 1. So whether you want to bring it out or not, that's up to you. I personally could care less. You could do either way. So it's your decision. You can decide what you want to do, but these are the minuses and pluses that were there. And this is the 4, this is the 12, this is the 8 that were inside the integral. They just left the integral because they had a variable accompanying them. So they were being multiplied with a variable, so that's why we can ignore them. The 5, it's up to you whether you want to bring it in or out. So, it's your choice. I'm going to leave it in for now. Eventually, I'll start bringing it out when we have more comfort with this kind of thing. But okay, so now what do? I have an antiderivative for t cubed. Well, I know what to do when I have a letter with a power. I'm supposed to basically take the existing power and add 1 to it. So the 4 is already there. It's going to get multiplied by whatever answer I get. So what's the antiderivative for t cubed? So t cubed becomes t cubed plus 1, and then I divide by the same value. So I keep repeating the same rule, which is rule number 2, as long as the power is not -1. So I first check the power. The power is 3, so I write it down and then add 1 to it, both in the power and then again on the denominator. Next, I have the 12 with the t squared. So again, the t squared, I look at the power. The power is 2, so it's not -1. So the rule is add 1 to it and divide by the same thing, 2 plus 1 and 2 plus 1. And if you want to write 3 directly, that's fine also. It's up to you. But again, the existing power, we add 1 to it. Next, we have the 8, and this one is a t next. So t, what kind of exponent does it have? Well, it's an invisible 1. So just know that there's an invisible 1 there, and it's not -1. So I use the same rule again. I take the existing power and I add 1 to it, and I do the same thing again in the denominator. So 1 plus 1. And finally, the 5. The 5 does not have any variables. So according to the rule number 1, so this is rule number 1 now, we just put a t next to it, and we put the plus c. The c is just the constant of integration. So c is a real number. Okay, so that's pretty much how that works. And, obviously I want to reduce it to lowest terms and make it look as pretty as possible. So I'm going to do that next. So first things first, let's add 3 plus 1. That's going to be 4. The next one is 2 plus 1, so t cubed divided by 3. Next we have t to the power of 1 plus 1, which is t squared over 2. And finally, there's the 5t plus the c. And obviously, we can now reduce the fractions. So when I have 4 times t cubed over 4, I can think of it like 4 over 1 times t cubed over 4. And really what I'm doing is I'm multiplying the numerators and I'm multiplying the denominators. Then I'm reducing these 4s to lowest terms. And when you divide 4 by 4, you get just 1. So the answer is just going to be 1t cubed for that whole thing. So in other terms, my first term is just t to the power of 4. The next term is 12t cubed over 3. 12 over 3 is going to be 4t cubed. And finally, 8t squared over 2. 8 over 2 is going to be 4. And the last two terms just copy down. So this is the answer. This is what we call the antiderivative. So this is what we call big F of x plus the little c. And this up here, the original number or the original expression that we integrated, it's called the integrand, by the way, is the little function f of x. So what you need to know again is that the antiderivative for the little f of x dx is the big F of x plus the c. Or another way of saying this using old notation is that when I differentiate the answer in the box, which is capital F of x plus c, I should see the original integrand, which is the little function f of x. So obviously that part in red that I just wrote at the end is not required to be written, but everything else on the page is required as part of the work. But obviously we're going to skip details later on once we're a little bit more comfortable with this whole thing. All right, so for part 3, we have something strange going on. We have a 7 over 3 and x5, and the x5 is in the denominator, and we're asked to integrate this part of the problem. So, and we're given a little hint that can help us out, but the bottom line is that it is bad for this x to be in the denominator. Whenever we're integrating, we want our variables to be in the numerator before we start the process of integration. So first thing I got to do in this problem before I start thinking about integrals is bring the x from the denominator to the numerator, and I do that by just giving it a negative exponent. So whatever exponent it used to have, just give it a negative, and now it's going to be in the numerator. So if you want, you can write 7 over 3 x to the negative 5 like this, but I prefer to write the x on the side just because I want to be able to see what the variable is and what the constant is, and the symbol in the middle is actually a product. So now that I know I can rewrite it in the numerator, I can start the process of anti-differentiating. So by the way, I can do this by the given rule. So this is what I did. I just used the rule to rewrite the x from the denominator into the numerator. And now I can say, well, there's a constant being multiplied with an x. So the constant is going to go outside, and the variable stays inside of the integral. So it's basically 7 over 3 multiplied by the integral of x to the negative 5. Okay, so there's only one term in this problem, so I don't have to use the sum or difference rules, but I'm just going to focus on the power. The exponent is negative 5. It's not negative 1, so that's great. So I could just write down 7 over 3 x to the negative 5 plus 1 divided by negative 5 plus 1. So remember, between the 7 over 3 and this in your expression, it's always multiplication, right? So that's what I write there. And where did this come from? This is actually rule number 2. When x is raised to an exponent, just give that exponent an extra plus 1 and divide by the same quantity. And obviously, I got to write down the plus c. And what is c? I got to remind the person reading this that c is a real number. So it's like an r with double edge on one side. From this point on, it's just going to be pure algebra. I need to clean it up as much as possible. So I only did calculus really in one step. And now let's just think about what's going on here. Negative 5 plus 1 is going to be negative 4. And then again, negative 4 in the denominator. We don't care if the exponent is negative, but in this problem, it's kind of nice to return it with a positive exponent since they gave us a positive exponent to begin with. So what I'm going to do next is just rewrite the problem with x back on the denominator. That way I can get rid of the negative 4 exponent and make it positive 4. The other thing I want to do is multiply the top with the top and the bottom with the bottom, just to make it as clean as possible. So first, the 7 is going to be hanging out there. When I bring the x to the denominator, it's going to become x4. It's no longer going to have a negative exponent, so this x to the negative 4 became x4 in the denominator. And the last thing I want to do is multiply the 3 with the negative 4. So 3 times negative 4 is going to be negative 12. And it's up to you whether you want to write the minus in front of the fraction or on the denominator. Just pick one of those two. I'm going to typically write it in front of the fraction just because that's the best way it looks. And then finally the plus c, and this will be considered the final answer. So this is how we treat the problem when x is written in the denominator. We just basically rewrite it in the numerator, we give it a negative exponent, and finally, at the end, we can return it back to the denominator to make the exponent positive, but really it's not required. We are very comfortable leaving the x in the numerator with a negative exponent, so don't worry too much about doing this last bit over here. But obviously, you have to multiply the 3 with the negative 4 to get negative 12. That's required, but bringing the x to the denominator is not really a requirement. Now let's look at example number 2, part 4. This is going to be most likely the most difficult one so far. And why is it difficult? It's difficult because I have a bunch of radicals or square roots. I have a bunch of x's in the denominator. So I have to be very careful with how I approach this problem. And I'm giving you a couple of hints here so you know what to do. So first things first, there's going to be a square root of x here. So how are we going to treat it? We need it to look like an x with an exponent. So we're going to use rule number 1 from the exponent world, which basically says write down the x and give it a fraction exponent. So remember, there's an invisible 1 here and an invisible 2 there. Those are usually not written down, but you have to know that they're there for the purposes of integration. So you're going to basically rewrite the square root of x as really x to the power of 1/2. Now there's also another square root in the denominator, which is the cube root of x squared. So how do we deal with that one? It's basically the same again. Apply the same rule, and the rule basically says you're going to write down an x in the base, and you're going to write a fraction power. Now, where's the numerator and denominator going to come from? The numerator is going to be the number on the inside, so that's what goes in the numerator, and the denominator is going to be the number on the outside, so the 3 is going to go underneath, and that's how you rewrite the cube root of x squared. Now, obviously, the cube root of x squared is in the denominator here in the original problem, so I'll have to worry about what to do with that later on, but that's how we rewrite the square root and the cube root with exponents that have power, that is a fraction. So let's take a look at the actual problem. So right now we have the integral of square root of x plus 3 over the cube root of x squared plus the 1 over x cubed and minus the 4x plus 1 dx. So this is the original expression that was given to me, and I'm going to shrink it down a little bit so that everything else can fit. I'm going to move it and shrink it down a little bit. But first of all, let's notice that we have, how many terms do we have in this problem? If you can count them, there's one term separating the first two, the one plus sign separating the first two terms, then another plus sign, another minus, and another plus. So we have a total of 4 pluses and minuses. So that means we have 5 terms. So we're going to need 5 integrals. One for the square root of x, and whenever you write the integral symbol, you're going to write down a dx at the end. There's a plus sign. We're going to need an integral for the 3 over the cube root of x squared. We need another integral for the 1 over x cubed. Another one for the 4x. And finally, another one for just the constant 1. So the original pluses and minuses are the places where the problem get separated. And what rule am I using to do this? I'm using rule number 6, basically, which is the sum difference rule. So if you have a plus or minus, you can break the integral apart. Now, using the exponent rule that we were given, I'm going to start by rewriting the square root of x as x to the 1/2. We need to do that so we can see the power so that we can use the power rule. Using the same rule, I'm going to do that here as well, but that one has an x squared with the cube root. So I'm going to write 3x to the power of 2/3. So that's what it would be like if it was in the denominator, but I want it in the numerator, so I'm going to add an extra minus sign. So it's negative 2/3. So the negative tells me that really this came from the denominator, and the 2/3 tells me that I had a cube root of x squared. Also, same thing is going to apply for the 1 over x cubed. The x cubed is in the denominator, but I need it in the numerator, so I'm going to write x to the power of negative 3. So the negative tells me that really it was found originally in the denominator, and I'm bringing it myself to the numerator. Next, I'm going to leave the 4x alone for a moment, and finally write down the integral of 1 dx at the end. So here, I did not use any of the integration rules. I just used a combination of these exponent rules to rewrite the problem with all my variables in the numerator. Remember, that's a requirement. I cannot solve the problem if I have 1 over x cubed, for instance. The constant rule does not apply, the power rule does not apply, there's no rule that applies. I need to write the x in the numerator first, so that's the reason why I'm adding the extra minuses in the 2/3 and also the 3. So now that we've done all that, we can apply rule numbers 2 and 1, but before, let's pay attention to the 3 here and the 4 there. They have an x next to them, so we can bring them outside of the integral. But I feel like at this point in time, we are able to mentally imagine that we brought them outside. We're not going to actually write a whole line just to do that. So let's do that mentally for a moment. And this is how we can start training on how to skip certain steps. So let's begin with x squared. Using rule number 1 and 2, we're going to solve the problem. Right now I'm using rule number 2. It says take the existing power and add 1 to it. So the existing power, we add 1 to it. It used to be 1/2. I'm just going to add 1 to it and then divide by the same exact thing. Now the 3, supposedly, I took it outside, and now I'm just looking at x to the negative 2/3. So again, it's going to be a fraction with the existing power, which is negative 2/3, and we need to add 1 to it, and we divide by the same exact quantity. So it used to be negative 2/3 in the exponent. We are going to do the same thing that we did for the first term, just add 1 to it and divide by the same number. Next, I have x to the power of negative 3. So again, it's going to transform into a fraction. The existing power is negative 3. Just add 1 to it and divide by the same quantity, just like we did for the first two terms. So the negative 3 gets a plus 1. Next, we have a 4x. So supposedly, we took out the 4, and now we just have an x to worry about. What's the exponent for x? Technically, nothing is written, so we know it's a 1. So according to the rule, just add 1 to the existing power and divide by the same thing. So the existing power is 1, and I'm just going to add 1 to it as before. And finally, I have the antiderivative for 1. This is where I get to use rule number 1. The antiderivative of a constant is just the constant times an x. And to finish it all up, I'm going to just simply add the plus c at the end. So plus c, and what exactly is the c? This c is the constant of integration. It's a real number, so that's how I say that. Okay, so at this point in time, it's a matter of cleaning up this massive mess that we have. So we're basically done with the calculus. From this point on, it's just pure algebra. And it might be a little bit tricky, but you can use your calculator for a lot of the stuff, right? So like, for example, 1/2 plus 1, it's 3/2, but if you didn't know that, you could just use your calculator. And again, it's the same number on the bottom, so again, 3/2 down here. Next, I have the 3 multiplied with x to the negative 2/3 plus 1. Again, what's negative 2/3 plus 1? It's going to be 1/3, and if you didn't know that, you can use your calculator as well. I prefer to write my fractions always horizontally. I don't like to write 1/3 like this, so I'm going to just keep always writing down the horizontal lines for my fractions. Next, we have x to the power of negative 3 plus 1. Well, let's just simply x to the power of negative 2 divided by negative 2. Next, we have 4 times x1 plus 1 is going to be 2, and divide by the same thing. And finally, there's the 1x. I can just simply write down x. We don't have to write down the 1. And there's the plus c at the end. Okay, so this is basically, so far it looks good. This is half the process. All I need to do now is kind of get rid of this 3/2 on the denominator. I get rid of this 1/3 on the denominator. There's a plus and a minus here. We can kind of combine them to make it a minus instead. There's a 4 and a 2 there. We can do something about that too. Maybe reduce it and get rid of some of those extra numbers. So let's focus on that. So what I want to do is talk about this part over here. So I'll explain it first, then I'll do it for the problem. So right now I have x to the power of 3/2 all divided by 3/2. So what I'm going to do for this problem is just pretend for a second that the x in the numerator actually is x over 1. And it's all divided by the 3/2. So I'm going to make it look like a fraction divided by a second fraction. And why am I doing this? I'm doing this because there's a rule from algebra that says what to do when you have a fraction divided by a fraction. The rule from algebra is basically ignore the first fraction and just, instead of the division that used to be there, write multiplication with the reciprocal of the denominator. So instead of 3/2, I'm going to write down 2/3. And this is now a product of two fractions. And how do we proceed forward? We just multiply the top with the top, the bottom with the bottom. So it's really going to be 2x to the 3/2, all divided by 3 times 1 is just simply 3. Some people prefer to write 2/3 of x to the power of 3/2. Regardless of how you do it, it's the same. So it's up to you. You can do either one. So in the future, I'm not going to write down all these details. That's way too much writing. That's way too many steps. So I'm just going to remember the effect. So if I have a numerator with x to the power of 3/2, what I'm going to do is just copy it down and just look at this number that's in the denominator. The fraction is 3/2. I'm just going to flip it upside down and write it in front. So let me show you how that's done on the next term. So I have a 3 already there, so ignore it for a second. Now I have x to the 1/3 all divided by 1/3 again. So how is it going to work? So I'm going to write down the x to the 1/3, that's the numerator. and I'm going to look at the fraction in the denominator, flip it upside down in my head, and write it in front of it. So that's a quick and dirty way of getting the same thing that we did over here done, but it's just a lot faster and a little bit more efficient this way. Now, for the next problem, I have plus and minus. So you know what? Let's just write down a minus instead. The 2 over here is not a fraction, so I'm not going to do what I did for the previous 2. I'm just going to leave it alone. I'm just going to write down the exact same thing, which is x to the power of negative 2 divided by 2 instead of a negative 2, because I'm putting the minus and the plus together to give me a minus sign. And finally, 4 times x squared, all divided by 2. Well, if you can reduce it in your head, that's great. 4 divided by 2 is going to be 2, so that's going to be 2x squared plus the x plus the c at the end. Okay, so this is pretty much almost the end. The only thing I'm going to do is think about what is going on there, 3 times 3 over 1. And maybe if you want, we can rewrite this part that has a negative exponent back in the denominator. Again, that's not required, but if you want to do that, be my guest. So let's finish it up and write down 2/3 x to the 3/2 plus 3 times 3 divided by 1. That's going to be 9 with x to the power of 1/3. And minus, and if you want, you can write 1 over 2x squared in the denominator instead of the x in the numerator with a negative exponent. This looks a little bit better because it has fewer minuses. And the other terms are not going to change, so we're just going to copy them all down. So this is as complicated as it will get in this course. This is really one of the high-level complicated problems. So you're not going to be expected to do too many of these things, but you should nonetheless know how to solve them because it's part of the work that you're expected to know how to solve. Okay, let's talk about part 5 of this problem, and this one is going to be easier compared to the previous one. We have an integral of 5 with e to the power of x, so this is an exponential function, and then we have the 7 being divided by x, and the whole integral is done. Again, there are 2 terms in this problem, and they're separated by a plus sign, so we're going to give each portion its own integral. So the 5 e to the x gets its own integral, and the 7 over x gets its own integral as well. So this is using the sum difference rule, which is rule number 6, if you want, if you're keeping track. You're not required to know the names of the rules and what their numbers are, but you are required to know what the rules do. So just know that there's a rule that allows us to separate integral. There's another rule that basically says if you have a constant next to x's, the constant can exit the integral. So I'm going to do that next. So I'm going to bring the 5 out and leave the e to the x alone inside the integral. And also I'm going to bring the 7 out and leave the dx and the other stuff inside. So there's an x on the denominator. I need to keep writing on the denominator. And when I bring the 7 out, there's nothing left in the numerator. I'm going to add the invisible 1 instead of the 7. So this is the same thing as 7 over x. Now, using my exponent rule, I can solve the first part, the antiderivative for e to the x. So what is the antiderivative for e to the x? The antiderivative for an exponential function is literally e to the x. This is one of the easiest rules there is. This is rule number 3 and 4 that we're using on this line. So I'm going to write down both of them. So the antiderivative for e to the x is just simply e to the x. This is rule number 4. And next, the antiderivative of 1 over x. So the x here is in the denominator. It has a power 1, so we're not required to bring it to the numerator like we did on the previous pages. That's because if I bring it to the numerator, the power is going to be -1, and I can't use the power rule. I have to use the special case of the power rule, where the exponent is -1, and this is just simply ln of absolute value of x. And then there's the plus c, and what exactly is c? C is just a real number. So every time I write a c that is not there, I need to add this portion, otherwise it's kind of incomplete. I have to say somewhere on the page what the c refers to. And really, this is it. So there's nothing else to do here. So I'm just going to write it one more time. It's 5e to the x plus 7 ln natural log, basically, of the absolute value of x plus c. So I didn't do anything there. I just wrote it all nice and pretty next to each other. But as you can see, the process of integration is a little bit tedious and there's a lot of steps, but eventually we're going to be trying to skip as many details as possible. So just look forward to that in the future. Okay, so earlier I told you that there is no product or quotient rule for the integrals. So the next example is going to help us know what to do if we see products or quotients in our integrals. So example number 4 says evaluate each integral, and again the question could be worded differently. You could say just integrate or solve or find the antiderivative. All those things are basically equivalent to one another, and it's basically asking you to find the antiderivative of what's written down on the page in front of you. So let's begin with the first one. The first one says the antiderivative of 3x plus 2, and this is being multiplied with 2x minus 5. And again, there is no rule for what to do when you have a product. So how do we deal with a situation like this? Well, what you got to do is actually just sit there and multiply everything out. So multiply the 3x with the other terms and then multiply the 2 with the other terms. So use your FOIL procedure to basically rewrite the problem as a sum and difference. So you can use the sum and difference rule. So let's begin with the 3x times 2x. 3 times 2 is going to be 6, and then x times x is going to be x squared. Then I have the 3x with the negative 5. When I multiply those, 3 times 5 is going to be 15, and the x goes for the ride. So that part is done. 2 times 2x is going to be 4x, and finally 2 times negative 5 is going to be negative 10, and I need to keep writing down the dx at the end. And now I'm noticing that the middle two terms are actually like terms, 15 plus 4. I mean, we can add those things. There's a negative 15x plus 4x. We can add them, so we instead of dealing with 4 terms, we could be dealing with 3. So that might be a little bit beneficial. So let's go on to do that. So negative 15x plus 4 is really negative 11x. And I keep writing everything else. So the 6x squared and the negative 10, they come along for the ride. And here we go. Now we have basically a problem with 3 terms and a bunch of minuses. So ideally what we want to do is break the integral into 3 pieces, one for the 6x squared, one for the 11x, and one for the 10. And then we bring the 6 and the 11 and so on and so forth out of the integrals. But I think we are ready to start skipping some details. So let's just pretend like we separated the 6x squared on its own. And once we separate it, the 6 can leave the integral and we just focus on the x squared. The x has a 2 exponent, so we just add 1 to it and we divide by the same quantity. So 2 plus 1. And if you want to write 3 directly, that's great, you could do that. Next, let's pretend like we have 11x alone. So the 11 is just going to chill, and we have x to the power of 1 next to it. The antiderivative for that is x to the 1 plus 1 divided by the same thing, 1 plus 1. And finally, there's the negative 10 written all by itself at the end. So what do I do with negative 10? It doesn't have any variables, so I just give it an extra x. And there's always the plus c, and what's c? C is the constant of integration. So this is basically doing all the rules that we learned just mentally, and just, you can see it's a lot more quicker this way. It's a lot more faster. The last thing I'm going to do is just write down 2 plus 1 is 3 and reduce any fractions that will appear. So then I have 11x squared over 2. Then I have the 10x plus the c. Those things are basically done at the end. And finally, 6x cubed divided by 3. 6 divided by 3 is going to be 2. So I'll just write down 2x cubed first. Then I have 11x squared over 2. Well, I can just write down 11 over 2, then x squared next to it. That way the number is separate from the variable. And that's not required. You can instead write 11x squared all divided by 2 like this instead. It's fine. It's also correct. It's up to you. Choose whichever one you prefer. and the 10x and the c to complete the answer, and that's basically it. So if I have a product, what do? I basically multiply everything out and then apply the sum difference rules and the power rules, exponent rules, whatever I need to do to solve and find the antiderivative. So next we have a fraction, x4 minus 1 divided by x squared. And again, there's no quotient rule in the world of integrals. So there's no equivalent to the quotient rule in the world of derivatives. So what do I do when I have a fraction such as this one and I'm supposed to integrate it? Well, basically, I'm supposed to divide it out. In this case, I got lucky because there's only one term in the denominator, so I can avoid doing long division. But if I have multiple terms in the denominator, then I would have to do long division. In this case, though, I can just write down x4, give it its own denominator, then give the 1 its own denominator, which is the x squared. So we can separate the fraction into two different fractions with the same denominator. Next, I'll just go ahead and reduce each of the fractions to lowest terms. So x4 divided by x squared is just going to say x squared at the end. 4 x's on top, 2 on the bottom. We can get rid of 2 on top and 2 on the bottom, and we'll just be left with 2 on the numerator. For the 1 over x squared, it is not beneficial to leave the x on the denominator. Remember, we're doing an integral at the end of the day. The x needs to be in the numerator, so I'm going to rewrite it in the numerator, but give it a negative exponent. So that's because it used to be in the denominator, but I want it in the numerator instead. So I'm using one of the exponent rules that we know from previous courses. And we also mentioned it on the previous page, by the way. And so finally, I now have an integral with basically two parts. One part for an x squared and one part with an x to the power of negative 2. Both of them will use the same rule of antiderivative, so I'm just going to take the existing letter and just add 1 to the power and do the same thing on the denominator. This x here has a negative 2 in the power, so just be a little bit more careful because you have to add 1 to the negative 2. And so negative 2 plus 1, both in the exponent and on the denominator. And also you need to add the plus c. C is just some kind of a real number. So we always have to write that down so that whoever's reading knows what the C stands for. Okay, the last thing I'm going to do is just reduce everything to lowest terms after I've added the numbers. So, 2 plus 1 is going to be 3. So it's technically x cubed over 3, but I prefer to write it like 1 over 3 x cubed. And then I have x to the negative 1 divided by negative 1. So a few things here. I'll leave it like this for a moment, but I prefer to, again, rewrite it. So first of all, there is a double negative situation going on. So the double negative situation will turn into a plus sign instead. So I'm going to do that first, get rid of the double negatives. And then I'm noticing that this x has a negative exponent. And we don't mind x's with a negative exponent, so you can just leave it as x to the negative 1 plus c and just move on with your life to the next problem. Or, if you prefer, you can just write it as 1 over x. So it's up to you. So I'm going to add the second answer, or I could just write down 1 over 3x cubed plus x to the negative 1 plus c. So either one of those answers is perfectly acceptable. Just pick whichever one you prefer and write it down. So you can either bring the x to the denominator and it loses the minus in the power, so it becomes plus 1, which we don't have to write down anymore, or you could just leave it as a negative exponent. It's okay either way. So which one should you do? It really doesn't matter. It kind of depends on what you're planning to do with the problem later on, if there's extra steps that we have to do. Sometimes in certain problems that we will do, there's a requirement to find the c at the end. So there's extra information that will be given to you, and we're going to do that actually in this section. They're going to give you some information to help you determine what c is, and maybe it's better to write down the answer with the 1 over x, but again, we won't know until we hit one of those problems, and we can decide at that point in time whether we prefer the first version of the answer or the second version of the answer. So for now, it's okay to leave it either way. Okay, so now that we've done all that work, let's do some application problems. And so here we go. It says a differential equation is an equation that involves a derivative of an unknown function. And we're supposed to solve these differential equations. So what we're basically given in these problems is basically some kind of function. This is what we typically called the little f of x. And they want us to find the big f of x, basically. So it's just presented a little bit differently. And when it's presented in this form, we call it a differential equation. So I could ask you to do either the antiderivative of 4x plus 3 and write the dx on the side, or I can tell you solve this differential equation, in which case you are required to come up with the notation yourself and basically do the rest of the problem. So the process is the same. You're integrating. It's just how it's presented and how it's being asked is a little bit different. And so it's called a differential equation because the dy over dx is written in front. This is what we call the derivative. So somebody's given me the derivative and they're saying we want the y, we want the original function. So how do I do this? Well, what we're going to do is the usual step first, which is to write down the existing problem. This is what they gave me. And what I'm going to do next is try to rewrite it. And how do I do that? I'm going to basically pretend for a moment that I'm multiplying both sides by dx. I would like to get rid of the denominator, basically. And so this step can be done mentally, but basically what I want you to do is think of it like dy equal to 4x plus 3 multiplied by the dx. And now you're kind of seeing where that dx was coming from in the previous problems. We always had to write a dx at the end, and you kind of know now, you can see where it came from. It's basically somebody doing this step for us. And so let me clean it up a little bit and write the x on the side instead of on top and as an exponent. And the last thing we do is just add the integral sign. Now, what's the antiderivative for dy? There's an invisible 1 over here, like I said before. The antiderivative for 1 is just 1 and give it the letter. So in this case, the letter is y, so I'm going to write down 1y. And by the way, 1y is really y, so eventually I'll get rid of the 1. And over here, now you can see we're doing just a normal antiderivative. There are basically two terms separated with a plus sign. So just individually handle each one by itself. So the 4x, we can kind of ignore the 4 and just focus on the x. The x has exponent 1, so we add 1 to it and we divide by the same quantity. Then we get to the 3. The 3 doesn't have any variable, so I'm just going to give it a variable. Which variable do I give it? I look over here, it says x. I need to give it the variable x. So earlier, over on the other side, I had the antiderivative of nothing but then dy. So I imagine there's an invisible 1, and I give it a variable. Which variable do I give it? I give it the variable that's written in the d part. So it says dy, that's why I wrote 1y on the next line. Over here for the 3, I needed to give it a variable, so I look on the side and it says dx, so I give it the variable x. And there's always the plus c, where c is just some kind of a real number. So this is supposed to be a capital looking R. I kind of butchered it, but that's what it's supposed to be. Like I said, 1y is really y, so I'm just going to write that instead. And next we will just add 1 plus 1, that's going to be 2, divided by 2, plus the 3x plus c. But really, in reality, 4x squared divided by 2, that's just the same thing like 2x squared, and then the 3x, and then the plus c. So how do you check if you're doing the problem correctly or not? Take the derivative of what's in the box, and you should see that. So let's try to confirm it. So let's confirm our answer. So let's see if we can confirm. What is the derivative with respect to x of y, where y is the answer that we came up with, 2x squared plus 3x plus c. So very quickly, the derivative of y is just 1, and then the inside part because of the chain rule, so 1 dy over dx. or just simply dy over dx. And the derivative of 2x squared is going to be 4x. The derivative of 3x is going to be 3. And the derivative of c, which is just a random real number, is going to be 0. But 3 plus 0 is just 3, so I could just stop it there. And you can see that this in the box is exactly what was given to us at the start of the problem. So that's how you can confirm that what you're doing is not nonsense, that what you solved for and what you got at the end is exactly the correct thing. So that's an example of how to solve a differential equation. And in the next part, we will basically look at how to find the number c that's missing. So far, every single problem, we just wrote plus c at the end and we didn't worry about it. We just said it's some kind of real number. But in the next problem, they're giving us some information. This is called the initial condition. And this initial condition is usually used to help you find the c. So you're going to do exactly all of these same steps. And once you get to the box and you want to call it a day and move on to the next one, you have to pause for a second and say, wait a second, they gave me initial conditions, they gave me some random numbers that will help me figure out what C is, and you're going to have to do that extra step at the end. So let's look at that example together. So okay, let's read example 6, which says, given f prime of x, which is 4 over square root of x, and f of 1 is equal to 3, find the function called f of x, small f of x. So again, the first thing I'm going to do is write down the given information, which is f prime of x is equal to 4 over square root of x. And my goal is to find just normal f of x without the apostrophe. So remember, apostrophe stands for derivative. So remember that this notation is really df over dx. So even though the information is presented a little bit differently, it's pretty much reminding us of what we did on the previous problem. We have df over dx equal to 4 over square root of x. So in other terms, I would like to know the little f of x function. So let me skip the f prime part and just write down this instead. So how do I find it? Well, first I need to get rid of the denominator dx. I need to remove that dx part. And so how do I do it? I multiply both sides by dx. And whatever you do on the left, you need to do on the right. And so this dx will cancel out the dx on the denominator. And so far what we have is df is equal to 4 over square root of x with the dx to the side. So that's step number 1, is just to rewrite the problem without the fraction. And the next step is to just add the integral sign to both sides to tell the world, hey, I'm about to do some antiderivatives. That's the only way to get the antiderivative. So again, just keep in mind that in the left side, there is no numbers or variables written between the integral sign and the df. That means there's an invisible 1. So I'm going to write down that invisible 1, and I need to give it some kind of variable. So what variable do I give it? I look over to the side. What does it say there? It says the letter f. So I just write down 1f. Now over on the right side of the equation, I have 4 over square root of x. And unfortunately, the x is in the denominator, so we have to do a couple of things. First, I have to rewrite it as x to the power of 1/2. So where did that come from? Just recall that when I have square root of x, it's really x with some fraction power. The 1 and the 2 are invisible, so we just write them and make it into x to the 1/2. But really, it should be in the numerator. So instead of writing x to the 1/2, I'm going to actually write down 4x to the power of negative 1/2. So where did the negative come from suddenly? It's to remind me that this x used to be in the denominator, but I'm writing it in the numerator instead. And then the dx at the end. Obviously, the 1f over here, we could just write down f. And if you like, you can emphasize that this is a function by writing down the small x. I won't do that right now. I'll do it at the end. But this is so far what we have. And so the next step is just integrating the right side. So how do I integrate 4x to the negative 1/2? The 4 is multiplied with variables, so I ignore the 4, and I just give the x some extra exponent. So instead of the original negative 1/2, I need to add 1 and divide by the same thing. So negative 1/2 plus 1. And also, I need to add the plus c to make it complete. Now you can use your calculator to figure out what negative 1 half plus 1 is, but hopefully you already know that negative half plus 1 is really just simply 1 half. And I'm supposed to divide by 1 half, but I don't want to do that. I don't want to have the 1 half sitting down here. It just looks weird. So what I'll do is I'll flip it upside down in my head and I'll squeeze it between the 4 and the x to the power of 1 half. So it used to be 1 half down on the bottom. So flip it upside down in your head. It becomes 2 over 1. And just write down over here in the middle between the 4 and the x. There's also the plus c at the end. Just keep writing that. By the way, 2 over 1 is really 2. So if you want to write down 4 times 2 instead, that will be perfect. And 4 times 2 is really 8. So I'm just going to write down f of x to remind you this is a function. It's 8 square root of x plus c. So this is the answer to the problem, but we're not completely done yet because in this problem we were told, hey, f of 1 is equal to 3. So we know that when I plug 1 into this equation, the result is a 3. And why are they giving me this detail? They're giving me this detail to help me figure out what c is. So you know what? Let's shrink this whole thing down so we can fit the rest of the problem. So I'll just move it across a little bit. And so I'm going to go up to here and say, but wait a second. I know that f of 1 is equal to 3. So in other terms, the x can be replaced with 1, and the result is that a 3 is going to appear. So in other terms, what we're saying is that 3 is equal to 8 square root of 1 plus c. So remember, we're replacing x with 1, and the outcome or the result is going to be 3. And so this equation has only one variable at this point, which is c. That's going to help me figure out what c is for this problem. This is not something we have to do very often in calculus, especially not in this course, but there may be time or two where you have to do it. So anyway, this problem, we have the square root of 1. The square root of 1 is 1. 1 times 8 is 8. So what number c gets added to 8 and results in a 3 at the end? Well, I'm just going to subtract 8 from both sides. 3 minus 8 is going to be negative 5. So c is negative 5. So we know specifically what the real number for this problem is. It's no longer just a random real number. It's actually really a negative 5. So the final answer, if you want, so what do I write down at the end for my final answer? I write down that the little function of x that we're searching for is 8 square root of x minus 5, because now we know what c is. And so this is the final solution that we have to present to the person giving us the problem. So everything else we had to do is basically just to get us to this point in time. Now the following two problems are basically exactly what we just did in the previous example part. So the only difference here is actually just more words are written down. There's a little story telling us what we're basically solving for. But in example 7, it says, suppose that the marginal cost of producing the x widget is given by c prime of x, and you can see the equation there. And we're told that the cost is measured in dollars. We are told to find the total cost function c. So again, we're given c prime of x, and they want to find c. So they want the letter not to have the apostrophe. They want us to undo the apostrophe. That means they want us to undo the derivative, basically. So that's the process of anti-differentiation. And we're told that there are some given fixed costs. So what does this mean? This means that even when you don't make any units, you still have to pay, or it costs you $5,000. Maybe this is to rent the place or to rent the facility where you're making the widgets or whatever. So this is basically telling me that the cost of 0 units is still going to be $5,000. So I have to pay that $5,000 no matter what I'm doing with my business. Whether I'm making a ton of them or not, I still have to pay that. So anyway, we are given c prime of x, so let's go ahead and write it down, which is 4x cubed minus 2x plus 1, and we want to know what c is. So I'm going to say I want the capital C of x. function, the cost function. So for this problem, I'm going to do the same thing that we did for the previous one. First, instead of the c prime of x, I can imagine that this is just the dc over dx. So this is basically just another way of writing the derivative. So you can either write down the apostrophe or write down the fraction notation. It's more beneficial for me to write down the fraction notation. And the reason why I'm doing that is because I want to remind you that we're going to multiply this side by the dx and this side over here by the dx. So let's just mentally do that. So this means that dc is equal to 4x cubed minus 2x plus 1 with the dx off to the side. And we can now just put the integral sign on both sides. So eventually you'll be able to just do most of this stuff mentally, so you don't have to actually write all these details down. But for now, I'm just going to keep writing everything down. And we start with the left side, the antiderivative of dc. So again, there's nothing between the antiderivative and the dc, so that means there's an invisible 1. So I write 1, and I need to give it a letter. So what letter do I give it? I look over to the side, and it says the letter dc, so I need to give it the letter c. So this is just simply just c. Or if you want to emphasize that this is a function, you can write down c of x. For now, I'll just write down c. And moving on to the right side, we have an integral, and we have 3 terms. So since we've done a bunch of these examples already, I'm just going to do things quickly here. First, starting with the 4x cubed, ignore the 4 and just focus on the x. It has a 3 exponent. We need to give it a 1. So 3 plus 1 is going to be 4, and we divide by the same number. So it's basically 4 times x to the power 4 divided by 4. Next, I have the negative 2x. So ignore the negative 2 and focus on the x. X has power 1 currently, so it needs to be increased by 1. So 1 plus 1 is going to be 2. And we divide by the same thing. So it becomes 2x squared over 2. And finally, there's the plus 1 at the end. So it doesn't have any letters, so I need to give it a letter. And what letter do I give it? I look over to the side, it says x, so I just give it the letter x. And I need to add the little constant of integration. I don't want to use c again because then you won't be able to tell which c I'm talking about. You're going to think that this c at the end is the same c at the front. So to make it less confusing, I'm going to write like a fancy looking c. So this fancy looking c is just the real number that always appears when we're doing antiderivative. And again, I don't want to write little c here and c there because they look the same and you might confuse them. I want this one to refer to the cost function, and I want this one to refer to the constant of integration. That's why I'm making it look kind of funny. So just so I can tell that this c is the constant of integration, whereas the first one is the function, in fact. Now, let's emphasize that it's a function by putting the little x, and let's go through this line and remove all the extra numbers that don't matter. So I have 4x4 all divided by 4. That's just simply x to the power 4. The next term I have 2x squared all divided by 2. That's just simply x squared. And finally, 1x. I could just write down just x. And finally, there's the plus constant of integration c. It's a fancy looking c this time, so I'm just going to write down the fancy looking c. So this is normally where the problem ends. However, in this problem, they gave me some extra information. They said when we make 0 widgets, we still have to pay $5,000. So why would they give me this information? They're giving me this information to help me determine what this constant of integration c is. So how does it work? This is saying that I'm supposed to replace x with 0, and the outcome is going to be 5,000. So the cost is 5,000 when the x's are all 0. So in other terms, 5,000 is equal to 0 to the power of 4 minus 0 to the power of 2 plus 0 plus the fancy constant of integration. So as you can see, this equation has only one variable, and so we can determine what c is, and that's the whole purpose of giving us that fixed cost sentence. So anyway, 5,000 on the left, 0 to the power 4 is 0, 0 squared is 0, and plus 0. All of this stuff is just 0, so I'm not going to even bother writing it down. So this is telling me that the fancy constant of integration is just really 5,000. So what's my final answer? So if somebody said, what's the cost to make the widgets in this company? I would tell them, if you want to make X widgets, then your cost is going to be X to the power of 4 minus X squared plus X plus the $5,000 that you have to pay no matter what. So this would be my final answer for the cost function. Okay, so we're finally on example 8, which is again another example with a story. So I'm going to give you a second to pause the video and read the story. But basically what we're dealing with is a marginal demand function, and we're asked to find the demand function. So pause the video for a second and read the question. So in this problem, the x represents the price of batteries, and the d prime is the marginal demand, meaning the derivative of demand function. And we're told that we are looking for the demand function. And also we're given some information. They're saying that 1,000 batteries are demanded when the price of the batteries is $3. So how do I say this? This is saying that the demand when the price is 3 is going to be 1,000 batteries. Remember, the price is X, so $3 is going to be the X. That's why I'm writing the 3 inside the parentheses, because that's where X usually is found next to the D. And the demand is going to be 1,000. So to save us a lot of trouble and to help us with these types of problem, I've been writing all the details, but I'm going to skip the details for this one and show you how I would do it. So I'm given the d prime of x, and it's negative 3,000 over x squared, and I want to know the d of x. So what I'm going to do is right away write down d of x, the demand function, and I'm going to just do all the other steps mentally. I'm just going to put the integral sign and the dx over here and write down the given information in between. So this helps me kind of avoid the previous lines where I would do all of this extra steps, where I would first write the c prime as dc over dx and then multiply both sides by the dx, then put the integral. I'm doing all that work mentally and just writing down the result basically. Now, it's just an integral at the end of the day with x on the denominator. This is bad. We don't want x in the denominator, so let me first rewrite it with x in the numerator, and we know how to do that. We just give the power a negative. So instead of having x squared on the bottom, we put x to the power of negative 2 on the numerator. And so, as usual, we can now ignore the 3,000 and just give the x an extra plus 1. So in the power, we're going to write negative 2 plus 1 and divide by the same thing. By the way, if you know negative 2 plus 1 is equal to negative 1, just do it right away. If not, it's okay. You could just do it in multiple lines. It's fine. And I'm going to use the fancy C again, just to keep it kind of consistent with the previous problem. So this is a constant of integration. And in this problem, we are basically going to find what C is, because they're giving us some extra details that will help us find out what the constant of integration is. But anyway, let's first clean up this massive mess that we've created. So first of all, negative 3,000, x to the power of negative 1, all divided by negative 1 plus the C. I don't like the fact that there's a double negative. That's kind of confusing. So I'm just going to ignore the double negative and write it down as a positive sign. So the demand function is going to be 3,000, and I could ignore the minuses at this point. And really, x has a negative exponent. If you want, we can write it underneath the 3,000. And finally, put the plus c constant of integration. So usually, this is where the problem ends. However, it's not over for this one yet because of the given information. So I'm going to write down, but wait a second. I remember you told me that the demand when the price is 3 is actually 1,000. So in other terms, if x takes on the value 3, the answer should be 1,000. So in other terms, I can say that 1,000 is equal to 3,000 divided by x, which is 3, plus the constant of integration c. So remember, x is the 3, and the result is the demand is going to be 1,000. And obviously, they're giving me all this information to help me figure out what C is. And by the way, 3,000 divided by 3 is going to be 1,000. So 1,000 plus C is equal to 1,000. So what does that mean? That means that C should be really 0. So my final answer is that dx is equal to 3,000 divided by x. And that's because the constant of integration turned out to be equal to 0.